Welcome to Comparative Anatomy of Vertebrates. Today, we're going to explore a fascinating topic called the jaw suspensorium. Have you ever wondered how a shark can thrust its jaws forward to catch a fish, while a mammal can crush hard bones? The secret lies in how the jaw is attached to the skull. By the end of this video, you will understand not just the biology, but the physics behind how different animals eat and survive. Let us dive in. To understand what the jaw suspensorium is, imagine you are trying to install a heavy, solid wooden door in your house. If you simply lean the door against the wall, it will fall over the moment you try to use it. You need strong metal hinges to firmly anchor it to the doorframe. In the vertebrate body, your lower jaw is exactly like that heavy wooden door, and your skull is the sturdy doorframe. The jaw suspensorium is the biological equivalent of those metal hinges. It is the specific anatomical mechanism that suspends the lower jaw to the skull, allowing animals to bite and chew. Now that we have a mental picture, let us look at the formal scientific definition. The jaw suspensorium refers to the complex of bones, cartilages, and ligaments that connect the mandibular arch, which forms the lower jaw, to the neurocranium, or the brain case. Interestingly, in early vertebrate embryos, the jaws develop from structures called pharyngeal arches. Specifically, the first arch becomes the mandibular arch, and the second becomes the hyoid arch. Over millions of years of evolution, the way these arches interact with the skull has changed dramatically, giving rise to the incredible diversity of vertebrate jaws we see today. Because evolution has modified these arches in so many ways, biologists classify jaw attachments into several distinct types. You will hear terms like amphistylic, hyostylic, autostylic, and craniostylic. While these words sound complex, each term simply describes which specific bones are doing the heavy lifting of holding the jaw in place. For instance, a shark uses a loose, flexible hyostylic suspensorium to thrust its jaws forward and grab slippery prey. In contrast, mammals like us have a rigidly fused craniostylic suspensorium, which is built to withstand the immense pressures of chewing tough foods like nuts or roots. This brings us to a crucial question. Why do different animals have such different jaw suspensoriums? To truly understand this, we must look at the jaw not just as biology, but as a mechanical machine. In physics, the jaw operates as a lever system, specifically a class 3 lever in most vertebrates. The jaw joint, which is the suspensorium, acts as the pivot point, or fulcrum. The jaw muscles provide the input force, and the teeth deliver the output force to the food. By changing the position of the suspensorium, evolution can drastically alter an animal's bite force and speed. To quantify how well this biological lever works, we use the concept of mechanical advantage. Conceptually, this tells us how effectively a lever amplifies the force put into it. The formula is Ma equals L in divided by L out. Here, Ma is the mechanical advantage, which is a unitless ratio. L in represents the in-lever arm, which is the perpendicular distance from the jaw joint to where the muscle attaches. L out represents the out-lever arm, the distance from the joint to the bite point at the teeth. If an animal evolves a longer in-lever, the mechanical advantage increases, giving a stronger bite. If the out-lever increases, the bite gets weaker but much faster. Now that we know the mechanical advantage, we can calculate the actual bite force an animal can deliver. The formula is F out equals F in times MA. F out is the output force, or the actual bite force at the teeth, measured in newtons. F in is the input force generated by the jaw muscles, also in newtons. MA is the mechanical advantage we just learned. This formula tells us in plain English that the final bite force is simply the muscle force multiplied by the mechanical efficiency of the jaw lever. If the mechanical advantage is less than 1, the bite force will be less than the muscle force, but the jaw gains a massive advantage in speed. Let us see this in action with a concrete example. Imagine we are studying a prehistoric reptile with an autostylic jaw suspensorium. We are given that the distance from the jaw joint to the muscle, the in-lever, is 4 centimeters. The distance to the front teeth, the out-lever, is 12 centimeters. The jaw muscles generate an input force of 600 newtons. We need to find the actual bite force. First, we calculate the mechanical advantage by dividing 4 by 12, giving us 0.333. Then, we multiply this ratio by the muscle force of 600 newtons. The result is a final bite force of 200 newtons. Because the outlever is long, force is sacrificed for a faster snapping speed to catch prey. So, we have seen how to calculate bite force for one animal. This brings us to a powerful application, mathematically proving how evolution shapes the jaw suspensorium for different diets. We will set up a comparative proof between two animals. Animal A is a hyostylic fish with a loose suspensorium and a short in-lever of 2 centimeters. Animal B is a craniostylic mammal with a fused suspensorium and a longer in-lever of 5 centimeters. Both have the same outlever of 10 centimeters and both generate exactly 1,000 newtons of muscle force. By keeping the outlever and muscle force constant, we can isolate and prove exactly how the evolutionary change in the in-lever affects feeding strategy. Let us continue our proof by calculating the mechanics for the fish first. We divide its in-lever of 2 centimeters by its out-lever of 10 centimeters. This gives a very low mechanical advantage of 0.2. Multiplying this by the 1,000 newtons of muscle force yields a bite force of just 200 newtons. Mathematically, this proves the fish has a very weak bite. However, the intuition here is that this low mechanical advantage allows its mouth to open incredibly fast. This rapid expansion creates a vacuum to suck in water and prey, which is a highly successful evolutionary trait for aquatic feeding. Finally, let us look at the mammal to complete our proof. We divide its larger in-lever of 5 centimeters by the same out-lever of 10 centimeters, resulting in a higher mechanical advantage of 0.5. Multiplying this by the 1,000 newtons of muscle force gives a powerful bite force of 500 newtons. By comparing the two results, we have mathematically proven a clear evolutionary trade-off. The mammal's craniostylic suspensorium provides a robust anchor further from the joint, sacrificing speed to gain the power needed to crush hard foods like seeds and bones. Now that we have proven the math, let us visualize these mechanics. On screen is a diagram of an animal skull acting as a lever. At the far left, the red dot marks the fulcrum, which is the jaw suspensorium joint. Moving forward along the jaw, you see a blue upward arrow, representing the input muscle force. The distance from the fulcrum to this blue arrow is the in-lever. At the very front, the green downward arrow shows the output bite force at the teeth. The total distance from the fulcrum to the teeth is the out-lever. This simple geometry dictates the entire feeding ecology of the animal. Before we conclude, we must appreciate one of the most beautiful stories in biology related to the jaw suspensorium. As the jaw attachment shifted in our mammalian ancestors to become rigidly fused, several bones that previously acted as the jaw hinges were no longer needed for feeding. Instead of disappearing, evolution repurposed them. These leftover bones actually shrank and migrated into the skull to become the tiny bones of the middle ear. This means that the delicate structures allowing you to hear my voice right now originally evolved as the jaw hinges of ancient fish. Let us summarize the key takeaways from our lecture. First, the jaw suspensorium is the critical anatomical bridge connecting the lower jaw to the skull, originating from embryonic pharyngeal arches. Second, we saw how it evolved from the loose, flexible hyostylic attachments in fishes to the highly fused, powerful craniostylic attachments in mammals. Third, by treating the jaw as a lever system, we learned that changes in the suspensorium's position create an evolutionary trade-off between bite force and feeding speed. You have now mastered both the biology and the physics of the vertebrate jaw. Excellent work!